Okay, so stop sharing. Let's share the new D command. Yep, awesome. Awesome. So I shared it with as a PDF, so we can, we will not miss any problems because as I told you, it is a platform, but it's the only thing available with the Microsoft team having a problem confirmed by the IT. So that's why I'm sticking with that. Okay, so you remember that questions that I got stuck on it because I did not read the point which not allow a serial input for both shift operations. So what I'm withdrawing my attack to the bug. Uh, I sucked that day, not the bug. Okay, so with regards to that question here, if you can see, allow a serial input for both shift operations. Okay, so what's gonna happen is, so like if you see that at the no change here, it's the next state will equal to the present state. However, when we do the shift right, instead of putting 0 at the most significant bit, we're gonna allow the serial input, okay, instead of a 0. Okay, now when it comes to 1 0, 1 0, we are doing shift left, and at the shift left, guys, what we're gonna do is we're gonna go to the left. Okay, therefore here instead of adding 0 or inserting 0, we're gonna insert what? The serial input. Okay, guys, and at 1 1, it's basically what the next state will equal to the parallel load as stipulated by the question. Okay, so we have 4-bit, so we need like 4D flip-flop. Okay, D flip-flops, and those flip-flops, they need to be connected to a multiplexers to allow a multifunctional design. So the since we have two mode control bits, okay, what we're gonna do is we're gonna use them as the selection inputs for the multiplexer. So let's pay attention to what is going on here. Okay, so at this is this. Can you see my cursor? Perfect, perfect. Okay, so this is the least significant bit. So at 0, look what happened. At 0, you are basically doing a loop back because the next state is equal to the present state. For the first flip-flop, for the second flip-flop, for the third flip-flop, and for the fourth flip-flop. Now, at 0, 1, which will allow the inputs 1 from each multiplexer to go directly where? To the D flip-flop. So what we are doing, look what we are doing. We are taking the output from this flip-flop to become what? To become the input here. Okay, that's giving me like A1 or Q1. Can you see that? Okay, now this is for here. For this multiplexer at 1, we're gonna take the input from the third flip-flop here. So boom, that's it. And for this one, we're gonna take it as from the fourth. And for this dude, what we're gonna do is we're gonna take the serial input. Okay, so it's an input bit. Okay, so you're gonna if you notice, sometimes we did the circulation, sometimes we inserted 0, and sometimes we we inserted the most significant bit as of the arithmetic shift. Okay, at 1 0, which is input 2 at the multiplexer, what we are doing here at input 2, we're doing the shift left. So what will happen is here at 2, I'm gonna have the input, the serial input, and for this one, what I'm gonna do is I'm gonna take the output from from the first D flip-flop to become my input here, because the next state for Q1 plus is equal to Q0, or the input at 2 should be equal to A0. Okay, Okay, and so on for the others. Now, when it comes to 3, okay, at mode 3, or when we have a selection input 1, 1, we're going to select the 3 at each multiplexer. So what we're going to do is we're going to do a direct load, okay? So we are loading, we're parallelly loading what the inputs that we would like to store it at the D flip-flop. So here, this is the least significant bit. We're going to have I0 at 3, I2 at I1 at the second flip-flop, the second multiplexer. Third multiplexer will have I2, and the fourth multiplexer will have what? I3. So the characteristic equation that we derived here are truly satisfied. All right. So let's move on to the another topic. So binary counters, they're nothing except like shift registers, but the way that the next state is going is incremented by 1. So let's suppose that like we consider this counters, okay, as a finite state machine. So the state diagram for the counters will be as the following. So if suppose that we have a 3-bit counters, so if we're gonna increase one at a time, so we are going from state 0, 0, 0, which is 0, to 1, 2, 3, 4, 5, 6, and 7. As you can see, we are what, guys? We are not missing any state here, okay? And therefore, there will be like 2 types of like counters. So the synchronous modulus counter we will have is like we will name that counter as a module 8, and at which, since we have 3 bits, and this is 3 bits, okay, that means like we're gonna have 3 flip-flop, okay? So 3 flip-flop will give you 2 to the power 3. As such, we're gonna have a state. We're gonna have a state diagram starting from 0 to 7. Okay. So the way that the next state is derived, that's our goal. That's our job. How we gonna derive it? Okay. It's nothing except that getting the getting the proper inputs for your flip-flop in order to force it to go to the next state. Okay. Now, counters is called fully sequence count. Okay, because look at this. We are going from 0 until we reach 7, and after 7, the counter resets itself, and then we're gonna do it again. Okay. Sometimes there is something called the truncated sequence count, at which you're gonna miss some states. Okay, don't worry about it. We're gonna I'm gonna show you how we're gonna design both examples. Okay, but I just want you to differentiate the between the 2 concepts. So at the truncated sequence count, look at this. So after I reach 5, I'm gonna go back to 0. It's not because it's a common fact. No, because sometimes I want you to design something, or we're gonna design something that go to 4, and after that go back to 0. The point is, at the truncated one, we gonna miss some states. Okay. A good example of that. Now, suppose we're gonna design a BCD counters. The BCD has, in order to be encoded, require 4 bits. Okay, and the BCD will go from 0 to 9, and after that, for the first digit, it has to go back to 0. Therefore, state 10, 11, 13, 12, 13, 14, and 15, we're gonna include them as a don't care. Okay, so let's take a look how we're gonna design a binary counters. Before we start with the design, and sometimes you can differentiate your counters based on the sequence that you are going through it. So sometimes you're gonna go from down up, which is the the normal human thinking. So we're gonna go from 0, 1, 2, 3, 4, and sometimes we're gonna go backward. So from 0, if you're gonna decrement by 1, decrement 0 by 1, considering that you have only 3 bits, it's like what? 0 minus 1 will give you what, guys? Will give you 7. Okay. because we have 3 bits. Okay, 3 bits. Sorry, we have 3 bits. If we are like as a human, we know that 0 minus 1 is equal to what? Minus 1. But since we're gonna do what? We're gonna decrement by 1. So the state that comes before 0 will be what? 1, 1, 1. And the state that will come before 1, 1, 1 will be 1, 1, 0. All right? So the design procedure for the synchronous counter is nothing except the same procedures that I shared with you guys, the same steps that I shared with you guys to design any sequential circuit. Okay, so you have to build the state diagram, and then if I did not ask you to choose the type of flip-flop, it's up to you to choose it. Okay, as long as you are abiding by the characteristic equation of each flip-flop. So if you choose D, which is the simplest one, so the next state equal to the input, and you boom, you're good. If you choose T, you need to go and grab the true, the characteristic equation of the T flip-flop, which is an XOR between the next and the next and the present state, in order to get the value of the input. Okay, now, and you need to develop the number, to decide how many flip-flops you need to include in your design. So in these 2 examples here, these 2 examples, we have 3 bits, so that's why we need 3 flip-flop. Okay, because each one of these flip-flop, let's suppose that we have ABC capable to encode what? Numbers up to 2 to the power 3, which is equal to 8, and that's why we're good. Okay, and after that, what we have to do is get the excitation table. Okay, the excitation table is what we're going reverse engineering. So we know what is the next state. Because it's a counter. We know that if we are going up, the next state from 0 is 1. So for A plus, B plus, and C plus, I know the value of it if I am at the current state A equals 0, B equals 0, and C equals 0. So based on that fact, can I get the flip-flop inputs? Yes, I can, because we have to go and get the excitation table of each flip-flop, and I can reverse and predict what is the input for the flip-flop based on my next state and the previous state, or the current state. Then after that, we can use Kernoff map to simplify the the Boolean equation for each input, and then after that it's nothing more than drawing the combinational circuit for each input. Okay, so let's take a look at this example. So this example, this is a fully module counter, fully sequence counter, and at which we are going what, guys? We are going up. Okay, look to the next. The arrow will determine what is the next state. Okay, so the next state here, it is 0, 1, 2, 3, 4, 5, 6, and 7. Okay, and at the exam, if I ask you to, as a short answer, you need to do this. Okay, like if you want to get the arrow is simply Alt 23. Okay, so, and after that, when you get to 7, say it again. Okay, buddy, like this. Alt 23. Okay, you're computer engineer or computer science or an engineer, so you need to know that. Okay, guys, we're gonna cover these later on. I'm gonna have a lecture just for the final exam. Okay, so don't worry about it. Okay, now, okay, so that is the state diagram in decimal, and this is the state diagram in what? In binary. So I know that if I am at, so what we're gonna do is I'm gonna write a table, and that table has the present state, the next state, okay, as well as what, guys? The input of the flip-flop. Now, please pay attention that I told you here to use a JK flip-flop to implement this synchronous counter. Okay, so you need to stick with the JK flip-flop. Okay, so now let's take step one. Step one is we already draw the state diagram of the synchronous counter, and this synchronous counter is going one at a time, and after we reach 7 we go back to 0. So how many bits do I need to encode this? How many flip-flop? Oh, perfect. We need 3 flip-flop. Therefore, I will, I will encode the most significant bit of the flip-flop to be A, B, and C. So this is exactly the present state. Now the next state, if I am at state 0, what will be the next state here? Will be 1. Therefore, I'm going to put 0, 0, 1. If I am at 0, 0, 1, what will be the next state, guys? 2. Therefore, I'm going to put 0, 1, 0. If I am at 0, 1, 0, what will be the next state? It's going to be 3. Therefore, I'm going to put here 0, 1, 1. And so on until I reach 7. Okay, at 7, 1, 1, 0, 1, 1, 1. What is the next state according to the arrow? It is 0, 0, 0, 0. Okay, guys. So now, because I know what is my next state, can I get the input for the flip-flop? Now, remember, I told you JK flip-flop. So each flip-flop has a pair of 2 inputs. So you're going to have 6 inputs to derive. Okay. Now let's go for A. So the flip-flop of A, we're going to pay attention just to the column of A at the present state and the column of A at the next state. Okay. So if I was at stage 0 and I'm still at stage 0, excitation table, thank you so much. 0 and 0, it's 0x. Boom, 0x I wrote here. Okay. If I am at stage 0, I'm still at stage 0, boom, 0x again. Stage 0 here at the third row, and the next state is equal to stage 0, 0x. Okay. Now state 0 and the next state is 1 according to the excitation table. Here I'm going from 0 to 1, it's 1x. Okay. Now if you I have spent over like 35 minutes over 2 slides, so please go back and read them. I'm not gonna re-explain them here. Okay. And everything is recorded. I have nothing to hide, guys. I gave you everything. Okay. Now, if I am at state 1 and I'm still at state 1, 1 and 1, x0. So 1 and 1, x0. Okay. State 1 at the present state, the next state is 1, it's x and 0 again. And it's going to be the same. Okay. Tuesday, I'm going to share with you a shortcut, but I want you to follow this. All right. So we'll do the same for B. So B, we are at stage 0, 0. Now we have like an input for we have JK for flip-flop B. Okay. So we'll do the same. So we have 0 and 1, 0 and 0. It's 0x at B. 0 and 1, it's gonna be 1x, and so on. And we'll do the same for C. You have to be careful and you have to not mix between row and columns, okay? Otherwise, it's gonna be a mess and you're gonna lose the mark. Okay, guys? So for C, we will look at this column and at this column, which is the present state, and at this column, the next state. And it was 0, it become 1. And here, what I'm gonna do is by looking to the excitation table, 0 and 1, it's 1x. I'm gonna put 1 here and x here. Okay. Now the question is, if it was a D flip-flop, instead of having 6 inputs, we're gonna have just 3 input, DA, DB, DC, and we will not bother ourselves to think. Okay, we're gonna just copy the next state from here. Okay. Okay, now we know what is we know the excitation table of our circuit that has that counts from 0 to 7. Now the question is, can I get the simplified version of each J and K in terms of the input? The answer is yes. Okay, guys? So how are we going to do that? What we're going to do is we're going to do a kernel map at which my input will be A, B, and C. Nothing else. Okay? So at each one, you know, like those, the column here and the arrow here is to label my input at the present state, A, B, C here. Okay? So look at this. At 0, 0, 0, what was the value of JA? 0. At 0, 0, 1, what was the value of JA? Still 0. At 0, 1, 0, what was the value of JA? 0. At 0, 1, 1, what was the value of JA? It was 1. That's why I put 1 here. And then it's don't care. So how can I group them? Just vertically. So the J of A can be derived by taking BC. We'll do the same for KA. Again, 0, 0, 0, KA was equal to X. Therefore, I'm going to put don't care. 0, 0, 1, K of A was equal to don't care. Okay, so don't care at the first, you know, like row. And then we're going to have 0, 0, 0, 1, and here, just 1 here, okay, at the 7. So KA is equal to BC again. Thank you. All right. Okay. And we'll do the same for B, for the J and K, for B and C. Okay. So suppose we did the kernel map. Okay. What will happen now is we need to design it. So we know that J of A, it's an AND between B and C. K of A, it's just a shortcut from whatever we did at J and A, which is an AND between B and C. JB is simply a loop back from C. And KB is the same. And for JC, C, thank you. I love you, C. It's just 1. Okay, so just have a VCC to the like, you know, to the input of the C flip-flop. Okay, so let's take a look here. So look what happened. Okay, now let's take a look at, this is C. So look, C, it's logic 1 for KC and JC. Okay, they're not singers, they're the input of the flip-flop. Okay, so and for B, it's just C. Okay, so you take a loop back here, and this loop back will go what to J and K. And for JA, it's an AND between B and C. So you take just an AND between B and C, and you connect it to J and K, and that's it. Now, you're going to have A, B, and C. Suppose that these are connected to a 7-segment display or 7-segment decoder. This, it's going to give you what, if you are at, I'm so sorry to, you know, like that we are through the COVID outbreak, but if you are at the lab and you have a 7-segment, after you design a circuit like this, it's going to give you like what? You know, like a counter. So 0, 1, 2, 3, 4, 5, 6, and 7, and then it's going to be the same. Okay. Now look, pay attention to the clock. So the clock, we have, you know, used what, guys, here? A negative edge triggering. So the thing is, I did not ask you to use anything. Okay, so you can choose whatever you want, but the most important part is that be consistent. So all of them has to be synced together. Therefore, all of them has to be either negative or positive. Okay. So that's it for the JK flip-flop. Now let's take a look at an example where we are designing a truncated one. So at the truncated one here, instead of going incrementing by 1, here I'm just, you know, like I'm arbitrarily going from one state to another. So I'm going from state 0 to 3, then to 5, to 7, to 6, then after back to 0. So it's going to be the same procedure like the synchronous the synchronous fully sequenced one, except the fact that at the first 2 parts of your table, okay, instead of going one at a time, we're gonna go based on whatever the state diagram here is showing, and some inputs we're gonna put them at don't care. Okay, so we don't care about them. So the first step is to write the what? So to write the state diagram. And since, look at this, you look at the maximum number that you have. So the maximum number that I have is 7. I need 3 to encode 7, and that's why I'm going to stick with 3 bits. Okay, and therefore I used to what? I used 3-bit to encode these states. Now there is 1, 2, 4. They're missing. So boom, don't care. Okay, right away. Okay, so now we're gonna write what these, like, you know, this the present state and the next state. We're gonna derive them from the state diagram. Okay, so look at this. If I am at 0, I'm gonna go to 3. I'm not gonna go to 1. Okay, if I'm at 1, where is 1? No 1. Shit. So what I have to do is to go to don't care. Okay, because I have no 1. 2, same thing. I'm gonna go to what? To don't care. If I'm at 2, it's don't care. It's indeterminate. So if I'm at 3, yes, I'm 3. I'm gonna go to 5. That's why I put 5. If I'm at 4, I have no 4. So what I have to do? Go to don't care. If I'm at 5, where is 5? 5 back. I'm gonna go back. Look at this. Back to 7 here. Okay, 5 to 7. If I'm at 6, I'm gonna go to 0. If I'm at 7, I'm gonna go to 6. Okay, please pay attention to these 2 big columns. Okay, present state, next state. Because if you did that, okay, the rest is similar to what I have explained. So now I know what is my present state and I know what's my next state. What I'm gonna do is I'm gonna derive the equation for each flip-flop. Now, like, let's take a look at C, okay, because that is the weird thing that you may encounter. So C or A, it was 0, it becomes X. So what are you gonna do, guys? You don't follow there. We don't have anything here. Okay, guys, look at this. Do we have any case to represent it was 0 and became X? Look at Q next and Q present. So like A, I'm looking at Q present and Q next. It was 0, it become X. Do I have anything? No. So again, I'm gonna put X. I'm not gonna bother my head. Should I put 1 or 0? Okay, no, just put X. And then at the kernel map, you're gonna use the X to your favor. Okay. So once we have the JK flip-flop inputs value, we're gonna do our kernel map again, and to get the value of what? Of JA, JB, JC, KA, KB, and KC. Okay. So look at this. Here, I like, you know, my goal is to group them in 8. I have this 0. Okay, this 0 is becoming, like, you know, annoying for me. Therefore, I can't connect them at group of 8. I'm gonna lower my bar. It's gonna be a group of 4. Yes, I can. These 4, it's this one and this one, so it's B. Now, again, I have 2 zeros here, so these, like, a group them aside, and it's gonna be just like C prime is not changing. Okay, that's why I put C prime. Now here, this is lovely. So it's only like I can group them in a group of 8. So it's 1. And for this, yeah, for this, okay, this is annoying. So for this one can be grouped in a group of 4. That's it, this way. And this one can be grouped in a group of 4 just this way. Okay, so I have 2 APIs. Okay, A prime, C prime, or you can do it using De Morgan as AC NAND, okay, and so on. So what you're gonna do is exactly what is, you have 3. You're gonna write, okay, draw 3 boxes, okay, and the most significant bit, stick with it, which is A, B, you know, the second significant one, and C is the least significant one. Okay, so what we're gonna do is, okay, it's here, A, B, C here. So what we're gonna do for A, it's what? B. So boom, from B I take it. The output of the flip-flop B will give me what? The input of A. And for KA, it's C prime. Okay, come on, give me the Q prime from here and connect it here. Okay, so, and we will do the same for the other flip-flop. Okay, so if you have this circuit and you connect them, you connect the output of this circuit, the output, I mean the Q of A, the Q of B, the Q of C. If you connect them to a 7-segment display, 7-segment decoder, you're gonna have something similar to what you got at your assignment 4, and you will have what? You will have, you know, like a sequence that is going from 0, 3, 5, 7, 6, and back to 0. Okay, so that's it for what? For the synchronous counters. Okay, so the BCD counters, as I told you, since we know that we covered the truncated mode, the BCD counters is a type of the truncated mode, because after we count, you know, it's a fully sequence till we reach 9, and after 9, no, we have to go back to 0. Okay, so what we're gonna do for that? Okay, and now here, look at this. Now I am asking you to design it using a T flip-flop. Okay, so the T flip-flop is, I'm gonna show you. We're gonna use the characteristic equation of the T flip-flop, or the excitation table of the T flip-flop, in order to derive the T input. Okay, so what is the maximum number of what's the maximum what's the maximum integer that I'm reaching in my state diagram is 9. So how many bits do I need to encode 9? 4 bits, because it's 1001. All right, therefore I need 4 flip-flops. So therefore I'm gonna, and I told you to use T flip-flop, so I'm gonna use it with 4 T flip-flops. Okay guys, now when I am at state 10, 11, 12, 13, 14, 15, I am in the indefinite state. Okay, so it's undetermined. My machine should not go to that state, therefore I'm gonna put X. Okay, so that's exactly how we're gonna do it. Okay, so now look at this. If I am at state 0, 0, 0, 0, okay, what is the next state? It's 0, 0, 0, 1, and so on until I reach to the state 1, 0, 0, 1. The next state should be equal to 0, 0, 0. Now when I have at the input 1, 1, 1, 0, 1, 0, here it's gonna be don't care, X's. Okay, okay, now by writing this state table, now I have to go do a reverse engineering. So I was, okay, let's take a look at, you know, Q0. Okay, Q1. Okay, we named it Q1 here. Okay, Q1 here, the present state was equal to 0, and the next state was equal to 1. What should be the value of the T? So since we have like 4 T flip-flop, the T for the least significant bit. Okay, so look at this. Next state was become 1. T should be equal to 1, because simply this is an XOR between Q and Q next. Okay, therefore I'm gonna put 1 here. 1. It was, okay, look, this is so funny. Okay, so each time here, the next state is the complement of what? Of the present state. Okay, so do I need to bother my head? I'm not. I'm gonna copy 1 everywhere. Boom. Okay, look, here it was 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and here it's 0, 1, 0, 1, 0, 1, 0, 1. So it's a complement. Okay, now 2, look at here. It was 0, then it becomes 0. So that means T should be equal to 0 according to the excitation table. So I'm gonna put 0 here. It was 0, it become 1. T should be equal to 1. Okay, it was 1. It was 1 here, and it stays 1. T should be equal to 0. 1 and 1, T is equal to 0. This is the case. Okay, guys, and so on. Okay, now for here, you know, like this state table is not fully written. At state 10, don't care. Next state, the input, don't care, and so on. Okay, So after that, what we have to do is to do a Kernoff map. Now we're gonna have like a 16 cell Kernoff map because we have 4 inputs. Now the input, okay, do not be fooled and put the input from the next state. No, the input should be from the current state, from the input. Okay, so that is exactly what we're gonna do. Okay, so let's take a look at T4. Okay, it's T4. So we have here we're gonna have 0, 0, 0, 1. So we have at the input here it's gonna be like our input. So 1, where is the 1 here? 1 at 3. Okay, so let's take a look at 0, 1, 3. Okay, I put 1 here, and I have 1 as well at 7. Oh, where is 7? Okay, that's 7. And okay, so the rest is zeros, and when I am at 10, 11, 12, 13, 14, and 15, it's x's. So how to group these two ones? Vertically. So what is the value here for this one? Okay, what is the value of T4? So here we are using what, guys? Look at this. We are using Q2 and Q1, okay? Because they're not changing the label of them here, okay? And so on. And look to this lovely one. You have don't care and ones, and you group them all in what? In one group. So this one group will give you Q4. Is that true? I'm asking you a question. Is that true? I'm grouping all these 16 and it gives me Q4. Are you serious? So if you group all the 16 cells, it's going to be 1, Tamim. So Tamim, all of them, it's going to be 1. So if you group the group of 8, it's going to give you 1 literal. If you group a group of 4, it's going to give you 2 literals. Okay? Okay. So after that, so we know what is the value of each input. So what we're going to do is we're going to implement them. Now, you have to tell me that, oh, that is my most significant bit, and this is my least significant bit. And look at this. So the input for the least significant bit, what was the input? T1 was equal to 1. Just put 1 here. Don't bother. Okay? And follow the same clocking technique that we have here. It's a negative edge. Okay? Okay, now look at this. For Q2, what was the value of T2? Q8 prime and the Q1. So you just do an AND. Okay, now if you are at the exam and I ask you to do this, okay, I don't want you to do the loop back. You're gonna I'm not gonna be able to follow with you properly. So what I want you to do, just put an AND between like what, Q8 prime and Q1. Do that and get it there. I understand that you meant to take the complement from Q8, which is this complement, and Q1, you took this Q1, okay? So now if we connect the output of this counters to a 7 segment, what's it gonna do? It's gonna count from 0 to 9, and after that it will not display nothing, okay? But what if I would like it to count to 10? What should I do? Can you answer this question? Add 10 to the table. It will not work because the 7 segment will not be able to display 10. Jason, thank you so much, buddy. So what we need to do is to have another circuit that will do the same thing. But now what we need to do is we need to have an output in addition to the next state. So the output, when we reach to state 10, the other diagram, the other block diagram of these 4 flip-flop will start working, and this one will stay at 0. Okay, and if we are at the next state, both of them will work, so will give me 1 and 1. So let me show you how. Okay, so what we're gonna do is, guys, we're gonna put an output, because after we reach 10, okay, that output will become 1. Okay, okay, guys. So the you know, like, it's still the same like input for T and for T and uh, for the T input for each flip flop. However, when we reach to 9, okay, guys, the output should be equal to 1 to let me know that I have already reached the maximum count of this block diagram. So what I'm gonna do is I'm gonna use this one, boom, take it to enable the second 4 flip-flop. Okay, so by inspection, let's take a look at 1. Okay, here. So according to the output here, okay, what is the equation for the output in terms of the input, which are the present state? So it's sum of product. It's just gonna be what? Sum of product is gonna be like Q8 Q8 Q1 and Q0 Q4 prime Q2 prime. Okay, guys. So okay, so what will happen is, look at this. So once I reach 9, or both of them like are this one are high and this one are high, this one will be activated, will send me an enable, and this one will start working. Okay, so after that, so instead of bothering myself and writing a big table, a huge table, okay, guys. So instead of that, and the table, what you have to do is you cannot go to state 10, because remember, the 7 segment will not give you like 2 digits. You need 2 digits, 2 7 segment displays in order to illustrate 2 digits. Okay, so we're gonna, like, use our smartness. Okay, so the smartness will say that after 9, okay, yes, I'm gonna go to 0, but let me have another bit that will be activated, okay, to let the other counter to work. Okay, so now this counter will start working. Like, suppose that you are at the lab and you did something through Altera and you create a block diagram of that. Okay, now, okay, and you have an enable. Okay, so you have an enable input somewhere, okay, for each one of them. Okay, enable. Okay, and now you created a block diagram. Now you need to use that block diagram to that enable input to your favor. So how are we gonna do it? So when I reach to 9, this one become 1 and this one will become 1. Y will be equal to 1. This BCD counter will start working with this dude. Okay, and by doing so, how many output I have? Look at this. I can project number with 2 digits. The maximum number of 2 digits will be from to 99. So 0 to 99 is going to be a mod 100. Okay, and it's up because why? Because I'm incrementing. Okay. Another 2 type of like counters that you may encounter in your, like, in the literature, is the ring counter. And the ring counter is nothing except a shift register. So the ring counter, look at this, the ring counter. So at the ring counter, the output of the first flip-flop will go, the output of the first flip-flop, boom, loop back to what? To the most significant bit 1. And then the most significant will be connected to the second one. The second most significant output will be connected to the next one. Okay, and so on. So what will happen? The following will happen. So let's suppose that you have 1, you input 1 here. Okay, arbitrary, assuming that we have 1 here. So what will happen is this one will keep going from, the one will keep going, but at each trigger, and this is a positive edge triggering, this one will keep traveling from this flip-flop to this flip-flop to this flip-flop to this flip-flop and back. Now the ring counter, this ring counter will be able just to give you one output high at a single time. Okay, therefore the state diagram will be what, guys? For that, if we started by 8, after that we're gonna go to 4, after that we're gonna go to what, to like to 2, and after that we're gonna go to 1. So you're dividing by 1 because you simply, like, you know, this is a shift to the right. You see that. If I do it the other way, I'm gonna what, I'm gonna multiply by 2. Okay, so by assuming that we have 1, so it's gonna be 1, 2, 4, 8, and back to 1. Okay, that is the ring counter. So to mitigate that, we have something called Johnson counter. Okay, and this Johnson counter, he thought, he looked at the ring and he told himself, okay, why do I need to make an assumption? Okay, what if I have 1 and I know how to get the 1 from this ring counter? Okay, it's by taking the Q0 prime and loop it back. Okay, so look at this. That's what happened to the Johnson counter. So the Johnson counter, for sure, we're gonna start by, if we have nothing, we did not connect anything to the flip-flop, we have 0, 0, 0, 1. Then after that, this the first clock cycle, the negative triggering, okay, the negative or the falling edge, okay, what will happen is this one will become 1 because this is 0, 0, 0, and this one, all of them are they're supposed to be the complement 1 and 1 and 1. Okay, this one will become the input here. Okay, then after that we'll start back as like a ring counter. So the 1 will keep going, and pay attention that we still have the complement. So after this is like, you know, this will become 1, 0, 0, and after that this we are taking the complement. So this one, when we complement it, it will become 1 and will be traveling to this guy. So it will become 1, 1, 0. Then we still like complementing them. So it will be 1, 1, 1. Now after complementing this one, we reach the 1, 1, 1. Now the complement will give me 0. 0, I'm gonna insert it at the beginning here. So what will happen? 0, 1, 1. Then after that, you complement this dude, this dude, this dude. You complement it and you shift it back. So it's going to be 0, 0, 1. Then you complement this dude and you shift it back to here. It's going to be 0, 0, 0. Okay. So the state diagram of the Johnson counter will be 0, then 4, 6, 7, 2, and 1. Okay. Using a D flip. Okay. If you wanna look at exactly what I have explained using the timing diagram, it's still the same. Okay, here. That's it for the course. Now, this you need to study it by yourself. I give it to you just, you know, to practice more. Now I have 4-bit. Okay, now this is not a fully sequenced circuit. Now this one is going from 0, is going to 0 to 8, to after 8 it's 12, then we have 13, 15, and so on. Okay, so we know that, oh, I'm gonna use a JK flip-flop, so I know that I need 4 JK flip-flop, and I need to get what the combinational circuit here, which is what is the value of each J and K, as we did. Okay, now I've done it with you using 3-bit. Now here it's showing using what, guys? Using 4-bit. Okay, so what you have to do is look at this. That is your present state. Exactly, you copy it as is. Okay, now the next state, what will be? So if you are at 0, the next state will become 1. Look, this is like, you know, more animated one. Okay, so the next state, if you are at 8, it's gonna be 13. So that's how you're gonna put it. Okay, if you did not follow with me. Okay, and if you are here, what will be the next state? The blue one here. Okay, so we are writing the state diagram. So after we write the state diagram and the states that we are missing, we don't care for them. What we need to do is to get the value of what? The value of the input for J and K for the 4 JK flip-flops to do what? To do the counter for, you know, the counter stipulated at this problem. Okay, so that is exactly what we're gonna do. So I know what is my present state. I know what's my next state. I need to get the input for each flip-flop. Okay. So after I get the input for each flip-flop, okay, what I have to do is to connect them. That's it. Okay, guys, that is for the course. I'm full of hope that you did understand, and you know, don't be scared from the sequential. It's nothing except a combinational, but instead of considering just input, we're gonna do okay. At this stage, we have a present state and the next state. Then at the second stage, we are doing the same thing. So that's it. Okay. Is there any question? Well, raise your hand so you can talk to me. Go ahead, talk.
Hello?
Yes.
Sir, can you go back to the T flip-flop question?
Which one?
Yeah, go down, not the T flip. Yeah. So in this question, why did you use your control your clocks, right? So instead of using normal clocks, you negated them like before. So
Why not? My answer to you, why not?
like like it's not a big deal because it's just active low and active high difference, but like why did you do it? It's just confusing.
Why not?
Mm,
Tell me. You have the question, so tell me, why not?
like it's just different. It's not because it causes any problems. It's
The
just different.
question that you need to ask me, did you follow the negative edge triggering for each one of them or not? If not, then I had a mistake. If I did, then why did you ask me? I can follow the positive, the edge, or the pulse.
Yeah.
I don't care.
Okay. So I was just making sure that it doesn't cause any like
It
problem.
does
Like
not cause anything.
okay.
Listen, let me ask you something, okay? So you're watching a match that is happening somewhere in Germany, okay? And there is a 5-second lagging between here and there, but the audio and the video are synced to each other. Does it matter
No.
to you? Huh?
No, it doesn't.
Okay, thank you so much. That's the answer.
All right.
Okay. Can you unmute yourself?
Yeah.
Please.
Yeah.
Go ahead, Jack.
All right, can you hear me?
Yes, I can hear
Oh,
you.
what was that?
Are you at the plane?
Okay.
No problem. No problem. Just go ahead. Proceed.
Sorry, can you hear me?
Yes, I do.
Okay, cool. So if can you scroll down to the last example? I had a question about yeah.
Let's do it. Yeah.
Yeah, I was just wondering what was that pattern for like the the like what were we trying to find here?
We will try.
Like the output.
Okay. Can you ask me the question and then mute yourself?
Yes. Sorry, what were we trying to find?
Okay. So we're trying to build a circuit. That circuit will output this pattern. Can we do that? The answer is yes. So what we're gonna do is we built a state diagram, and from the state diagram after that, go to the step-by-step here, showing here at the animated note. And after that, what you need to do is to get the input equation for each flip-flop. Once you have them, okay, now you have 4 JK flip-flop, connect them properly, and this synchronous 4-bit circuit will be like, you know, a 4-bit counters that will produce the state diagram given at the example here. Is that clear?
Yep. Good.
Okay, any other question regarding the material? So if you want to ask me, please enable your mic. Raise your hand. Sayyidi, raise your hand. Okay, you can talk. Can you ask me?
Oh, sorry, I forgot to unmute myself. It's about the final exam. If you're willing to have an Adobe Connect with us.
No, please. I'm gonna stop you. It's not about the final now. Okay. Do you
Okay, I
have
understand.
regarding the material?
No, thank you, sir.
Okay, then wait to the end then for the final. Okay. Okay. Any question regarding the content we have covered today? Raise your hand. Dami, raise your hand. Go ahead. Will we always be provided a state diagram when doing a problem related to counters? Depends. But if I'm going to ask you to design a synchronous counter that will do the following, you need to go ahead and design it. So I already give you the state diagram. Okay. Now, let's say that I would like you to design a sequence counter, a fully sequenced one that has 3 bits. You need to derive it by yourself. You need to think. So 3 bits, it's 7. Okay. So fully sequenced from 0 to 7. If it's a truncated one, yes, I need to give it to you. Okay. If you need to you need to enable your mic. I already give you the right to enable your mic. The Johnson counter, your question is vague. The Johnson counter is a special type of ring counters. However, look at this. What we're doing is we're connecting the complement of the least significant bit back to the input to the most significant bit. So starting by 3 zeros, what will be the next state? Okay, the next state, okay, like we have zeros here. So we complemented this and it become the input there. So it's gonna be the next state, it's 1 0 0. Now we're gonna complement this again and do the shift to the what? Look where is the direction? The direction is you're going to the right. Okay, so do the shift again. So it's gonna be 1 1 0. Okay, complement this 0 again and shift it back while shifting these two one position to the right is gonna be 1 1 1. Now complement this, which is the one here, and shifting the other two one position to the right, it's gonna be 0, 1, 1, and that's it. Is that clear, Daimi? For the Johnson counter. Exactly. Thank you. Yes. Okay, Ghazal, go ahead.
Hello.
Yeah.
Sorry for the you said for one of them that we connected from the output to the connect to the input. You said if we have this kind of question, we need to write it in the final exam. It was a little bit up.
What is odd, Ghazal?
No, I mean like I don't understand how to like.
Okay. Now let's suppose that I told you I want you to do the following. So you have a 3-bit Johnson counter designed by a D flip-flop, okay?
Okay.
And you want to give me what are the, the count sequence of that Johnson counter. Okay, so 0, 0, 0. Okay, look at this. 1, 0, 0. I'm typing. Okay, 1, 1, 0. 1, 1, 1. 0, 1, 1. Okay, 0, 1, 0, 0, 1. That's the answer. I did not need anything except my keyboard.
No, sorry. Like it was like you said instead of connecting, for example, Q to the beginning, we just have to write it because it's hard to follow the diagram if we have to draw something.
Thank you. Okay, so let me tell you something. Look at this. So this is done through through a software, okay?
Oh, okay.
Now you using a pencil and paper method, you're gonna create a mess, a big mess.
Yeah.
Considering the fact you will be stressed using the exam, because the exam is stressful. I don't know why. It's stressful all the time. People are stressed by the exam. So in order to relieve that stress, I don't want you to do a loop back. So go here. T is equal to 1. Just connect to 1. So you derive that the T for the second flip flop is equal to Q8 prime and Q1. So just do an AND.
Oh, okay.
Okay.
Thank you so much. Thank you.
So disable your mic. Do you still have a question, guys? Do you have any questions for the material provided today? Material, okay? Does it matter which flip-flop we're using when making a synchronous counter? Or, okay, unless specified by the question, you are free to use whatever you want. And each time you need to stick with the input. So you remember at the JK, we have J and K for each flip-flop. For the T, we have only 1. And the way we derive it using the excitation table for each one. You have to stick with that. And, okay, now, I think this is like a very smart question. You can, you know what? Shan. Okay, let me go here. Okay, you can decide that this dude can be like a D flip-flop. Yes, but as long as at the table here, you specify that this is D and you copy everything. So it doesn't matter. You can have any type as long as you're following the state table you design it for. You design it above. Okay? Do you have any question, guys? Do you have any question regarding the material from Week 1 up to date. If you have a question, I can stay with you to the night. Let me know. Do you have any questions for the materials? The content. Don't ask me about exams and you don't want to know things. Content. I care about the content. Rawan, raise your hand. Raise your hand. Go ahead, Rawan. And guys, make sure not to leave.
Hi, can
Yeah,
you
go
hear me?
ahead. Yeah, Rawan. What's the question?
Yeah. Um, I have like some problems in module 5.2, the second module of the fifth module, part 2. Um, I just like feel a bit lost in it.
Can you
I don't
point
know.
which slide, which note? 5.2. Okay, which note? Which slide? Not tell me.
To be honest, like I don't know. I just feel like a bit complicated about it. I don't understand it fully. So like,
Okay, you need to bring a coffee,
mhm,
relax, and watch the lecture and go step by step.
okay,
Okay? Or just send me an email, Roman. Okay?
okay,
Okay, don't worry about it. But
okay.
your question is big.
Yeah, because like
It's not
I
something like you need to be sharp. Okay? You tell me like at this slide, I don't understand. At this point, at this minute, I don't understand. But don't tell me that I don't understand it all. So
okay, I'm
tell me
gonna
like,
re
have you watched it? Where exactly you did not understand? That's exactly the type of question I would like to hear now.
to be honest, like I just feel somehow like not sure. Like when you gave, for example, the last example in slide 18.
In
Um,
module 2, module 5-8.
yeah,
Okay, which one? Example 1.
yes.
So, Raman, did you understand the lecture today?
Um, not a lot. I'm gonna rewatch the lecture today, actually.
Okay, so basically here, the question exactly here, instead of designing a counter, you're gonna design a circuit that only give you 1 when you are at state 3.
Okay.
Okay, so you have 4 states. Okay,
Mm-hmm.
S0, S1, S2, and S3, and they're going each one to each one of them. Okay, and you're gonna get
Mm-hmm.
like 1 at the output, like at state 3, as long as you're staying at state 3. Okay, so given that you have the state diagram, you have this state diagram, you're not capable to go and design the circuit.
No, I can, I guess.
Well, okay, watch the videos again and email me. Okay, Tuesday I'm gonna review 5 and 6 for you, Rowan. Okay, is that good?
Okay. Yes, okay. Thank you so much.
Any other question, guys? Okay, can you make it easy on yourself and raise your hand? That's it. What are you gonna type? Do you have any question? Okay, for that question, I'm a little confused when we have an output connected back to the input. How do we find the initial value? There will be no initial value. So you need to watch my lectures at which we designed the SR latch, okay? So we made a hypothesis. Suppose that the value was equal to 0 and the value was equal to 1. We only care about the convergence, the stable state, and we give them, okay? You're still thinking as a human. You need to think as a machine. Okay? So, like at the SR latch, so suppose that S was equal to 0 and R or P was equal to 1. What is the value? Does it change? And then you counterattack because, like when you have the loop back, if the value is keep changing, that will create a bouncer. Not any type of a loop back will create a sequential circuit. That's why we have those 4 types. If you remember the case of 1 and 1 at the input of the SR latch, it's no longer a latch. You need to enable, listen, okay, you're taking so many times. You need to enable your mic, okay? Can you enable your mic and that's it? Any other questions? From Ariani up to Yichen. The quiz will be on Adobe Connect. It will not be on a Brightspace. That's the announcement. Okay? How? It's up to me, not to you. Okay, so would you like it to be on Tuesday or Friday? Yeah, Sayed, I'm gonna get back to you, man. I'm gonna get back to you. Sayed, I'm gonna get back to you. Don't worry about it. Friday is better, okay? So we're gonna stick with Friday. The time for the quiz is Friday. So what you need to do is just, you have a regular lecture on Adobe Connect. Go and connect with me. The last 2 months, yeah. Do you have any other question, guys? Louisa, raise your hand. The format of the quiz is up to me again. It's a quiz. So what about if I share the exam with you now? Yeah, this is a mandatory quiz. Now, let me reformulate your question, Rawan, okay? So the question, the correct way is, are you gonna ask us something out of the material or within the material? Are you gonna bring us an exam, like an exercise or a questions outside my material or within the material? The answer will be within the material. Next Friday, yeah. The material includes my talk, my notes, Ala talk, labs assignment. Guys, the decision to move it to Adobe Connect, it is to your favor. Trust me. Trust me, it's gonna be to your favor. 100%. 20 minutes. The final is similar to what we have. Okay, we still have a week, okay? We still have a week. We talk about the final later on, okay, guys? We talk about the final Friday, next Friday. So Tuesday, we're gonna do a review together. We're gonna solve the final that the other 3 profs, they give it within the winter. Okay? And, or I think I'm gonna do a review and prepare a video for you for the final. And that's it. Now, when it comes to the material, there will be no new materials, except you're gonna have a DGD, which is, you know, a practice to whatever we covered at module 6, and that's it. Two modules will be using Adobe Connect. If you will not be live with me on Adobe Connect, you will not be able to write the exam. Just to be clear, I don't need your camera. Cool? And you know what will happen? Okay, you know what? I'm not gonna be a jerk. I'm gonna tell you exactly. So I'm gonna break you into 2 or 3 breakouts. Each one of them, I'm gonna upload like the exam with it. Okay? And you're gonna have 20 minutes if you are not a SAS student to go and submit it while you are with me. So you're gonna ask me. Okay? So it's gonna be long answers or short answer. I don't know. The question is gonna be within the materials? That's the answer. Yes. And I'm gonna write it in a way that everybody will answer. Okay, guys? Don't worry. So there will be no time. So I'm gonna say start, then the quiz is done. If you are a SAS, you count the time from the starting point, apply it according to the Ventus website. Okay, I do have an access to the Ventus website. So let's suppose that X has 33%. If he submit before the 30, like, you know, 1.33, he will be fine. After that, it's gonna be late submission. Okay. Yes, quiz will be submitted on Brightspace. Lectures will be live forever from now to the end of the course till Friday. That's it. I want to ask you, do you have a question? And basically your questions is how to, like, can you give us the style of the exam? Can you give us the exam itself? You know, like, guys, you're engineer and you're studying at the University of Ottawa. You're not studying somewhere at. So leave the exam to me, leave the grades for me. You know, like people who talk ITI 1120, they know me. So I'm not gonna like fail the whole course. The book. If you feel lost, you read the book. And let me ask you something, Rawan. Did you watch Ala DGD's? So he prepared, like I sent him some problems and their answers. So you need to watch it and go, like, you know. How can I, if I understood the material, and can I, yeah, of course you can solve the quiz. The quiz will be from the material, guys. So, okay, guys, when it comes to the final exam, this is my philosophy. I want to give you a balanced exam. If you watched my lectures and you did the assignment yourself, you're going to get a straight A. If you are a lazy dude and you did not study nothing, you're going to fail. If you're gonna like, if you're a cheater that you wanna go and look for answers, you're gonna solve 2 questions and the exam will run out. Or I can give you like a take-home exam, but let me tell you something. If you like, all of you, if you like sit together to solve it, you will not be able to solve it. So choose. You know, I'm not the guy who put the examining criteria. So the quiz, I guarantee 100%, 100%. I swear on my mother's heart, like this. It's gonna be from the quiz, from the materials, similar to the examples that we covered together. You want any more like guarantee like more than this? Yeah, wait to the Adobe Connect, okay? Yeah, that's it. That's the announcement I made. I made the announcement. It's about the quiz. The quiz is gonna be over Adobe Connect 24th. It's gonna be something similar to the lectures that I have covered with you guys. Okay? And I wish you a very wonderful day, okay? Okay, guys? And, you know, I did my part, okay? Now you have 2 things to do, guys. Okay, Rawan, just send me an email. Like I told you what we're gonna do. Send me an email, Rawan. There is 2 things. I'm gonna upload the statement of integrity. You need to download it, sign it, initial it, and submit it as an assignment. Okay, as well as I told you, like, you would like to ask me any questions, come and ask me. But at the same time, I'm very disappointed to see that only 30 out of 145 evaluated the course. So you think it's like an Amazon review? You want to wait until the end? Okay, guys, if you have any questions, come and ask me. And I need Sayed now to talk to me. Sayed, go ahead, man.
Can you hear me now, Professor?
Yes, I can.
Okay. I remember you mentioned something that we can have a call during the exam, just in case any of the students are having any confusions or not understanding the questions. I was wondering if you still will consider that for the final exam.
Well, we will, like, that's why I'm gonna do the quiz using Adobe Connect, is I'm gonna do it as a prova, and after that I'm gonna answer. That's why I told you to wait, okay?
All right, sounds amazing. Thank you so much, sir.
You're welcome. Okay, so you don't have any questions, you have another lectures, go ahead, enjoy your time, take it easy, and have a wonderful day.